In this episode, we will talk about SmolVLM, redefining small and efficient multimodal models. So these large vision language models, VLMs, they're doing some pretty amazing stuff, right? Letting computers really understand images and text.
Absolutely. The capabilities are impressive, no doubt.
But there's always a catch, isn't there? These big models, they need serious computing power, loads of it.
That's the crux of the issue, yeah. They demand significant resources, which really limits where you can actually use them. You're not running them easily on your phone or, other edge devices.
Exactly. It's like great tech, but stuck in the data center mostly.
And the thing is, when people have tried to make smaller versions, they often just, scale down the big designs.
Kind of like a shrink-ray approach.
Pretty much. But that often keeps some of the inefficiencies, especially around how images are tokenized, broken down. It ends up eating a lot of GPU memory, which is exactly what you don't have on smaller devices.
Right, not very practical then. Which I guess brings us neatly to SmolVLM. This sounds different. Not just smaller, but smarter.
That's the goal, yeah. It's about rethinking the design specifically for efficiency.
So what did they do? How did they approach this?
Well, they were really systematic about it. They looked into different architectures, different ways to handle the image and text data, the tokenization strategies, and even how to pick the best training data. The whole focus was minimizing that computational overhead.
Trying to get the most bang for the buck, computationally speaking.
Precisely, making them lean and mean enough for less powerful hardware.
And it sounds like they landed on some pretty key insights. Finding design choices that really boost performance without needing tons of memory.
They really did. The results are quite something. Their smallest one, the SmolVLM 256M, it uses less than a gigabyte of GPU memory when it's running.
Wow, okay. That's tiny for these kinds of models.
It is, and here's the kicker. It actually outperforms a model called IDFix 80B, which is, get this, 300 times larger.
Seriously, 300 times, despite an 18-month gap in development, too.
Yeah, it really underscores how much difference designing for efficiency makes, rather than just scaling down later.
That's incredible. A real David and Goliath situation there.
Yeah.
And it's not just the tiny one, right? Their bigger SmolVLM model is also punching above its weight.
Correct. The 2.2 billion parameter version holds its own against state-of-the-art models that need twice the GPU memory.
And they handle video, too.
Yep, video understanding is part of the package.
So the core idea, the big takeaway, is that smart design architecture, tokenization, data can get you really far, even at a small scale.
That's it exactly. It makes deploying this kind of AI on, say, your phone or other edge devices seem much more realistic, practical, energy efficient.
And they've opened it all up. Models, code, data.
The whole lot. Model weights, data sets, the code, even a mobile app demo showing it running on a smartphone. It's all open source to encourage more work in this area.
Fantastic. Okay, let's really dive into the nuts and bolts then. Remind us, what was that core problem they were tackling?
Fundamentally, it's the need for VLMs that can run effectively on devices without massive computing resources.
Yeah.
Phones, smart cameras, sensors, places where power and memory are tight.
Right, the edge.
Exactly. The current giants are just too power hungry. And as we said, just shrinking them doesn't really cut it. You often end up with inefficient designs.
So how is the SmolVLM architecture different? What's under the hood that makes it so efficient?
Okay, so they have a pretty clever way of handling the visual side. For images, especially high-resolution ones, they don't just feed the whole thing in, they split it up.
Like into tiles?
Sort of, yeah, into sub-images. For videos, they found that averaging frames together, which some models do, actually hurt performance for these smaller models. So instead, they just sample individual frames.
Okay, so you break down the visual input. Then what? An encoder processes these pieces.
Right. A standard vision encoder turns these sub-images or frames into visual features, but then comes a really neat trick.
Here we go.
They use something called pixel shuffle. Imagine you have your grid of visual features. Pixel Shuffle rearranges them. Think of it like taking say, a wide, flat grid of tiles and restacking them into a narrower, taller pile. You trade spatial resolution for more channel depth.
Okay, so less spread out, more depth of information at each point. Why do that?
The big win is reducing the number of visual tokens, or the chunks of information, the model processes. Fewer tokens means much less computational work, especially for the attention mechanisms later on, which look at how different tokens relate to each other.
Got it. Less work for the attention part.
Exactly. After the shuffle, the features get projected into a format the language model understands using an MLP that's a multi-layer perceptron, a type of neural network layer. These become the visual tokens.
And these visual tokens then get mixed in with the text.
Yep, they're combined with the text embeddings, the numerical representations of the text, either just stuck together end-to-end concatenated or sort of woven together interleaved.
And that combined stream goes into their language model.
Into their SmolVLM2 language model, yeah.
Right.
And that produces the final text output, like an answer to a question or a description.
Okay, that makes sense architecturally. Now, they mentioned several specific novel contributions or key design choices. The first was about balanced encoder LM parameter allocation. What's that about?
Right, so you have the part that sees, the encoder, and the part that reads and writes, the language model. How big should each part be relative to the other, especially in a small overall model?
Does it matter? Can't you just have a really good encoder?
Well, they looked into that. They found if you pair a really powerful large vision encoder with a tiny language model like their 135 million parameter, one performance actually dropped.
Oh, interesting. Why?
The thinking is the language model just doesn't have the capacity to make full use of all the super detailed information coming from the big encoder. It's like trying to funnel a river into a garden hose. It's inefficient for these compact models.
So smaller encoders were better.
For efficiency in compact models, yes. They found smaller encoders, like a 93 million parameter SIGLIT model, struck a better balance. So, finding one, balance the parameters between the vision and language parts. Smaller encoders are often better for compact, efficient models.
Makes sense. Find the right balance. Okay, next point. Extended context length. Why does a VLM need to handle a long context?
Well, think about an image. Even after you process it down, it can represent a lot of information. A single 512 by 512 image could easily become over 1,000 visual tokens.
Right. And the text prompt or question could be long, too.
Exactly. Their initial language model, SmolVLM2, could only handle 2,000 tokens at once. That's often not enough to see the whole picture, literally, and process the text.
So they needed to increase that.
Yes, especially for their 2.2b model, they pushed it up to 16,000 tokens. They did this by tweaking the rope E, that's rotary position embeddings. It's a method models use to understand the order of information. Extending the base lets it handle longer sequences.
And did that help performance?
Significantly, as you'd expect. Which leads to finding two. Compact VLMs really benefit from longer context lengths. They can just handle more complex inputs.
Okay, third point. More aggressive visual token compression using that pixel shuffle thing. You mentioned smaller models benefited more from this.
Yeah. Remember, pixel shuffle reduces the token count by a factor of the shuffle ratio squared, R squared. Larger models might use a ratio of, say, R2.
But for SmolVLM.
They found that for the smaller SmolVLMs, a more aggressive ratio of R4 worked better.
Why compress more if it might lose detail? Isn't that counterintuitive?
You'd think so. But in small models, the attention mechanism's computational cost is a bigger relative burden. By drastically cutting the token count with R4, even at the cost of some spatial detail, you reduce that burden significantly. It lets the limited capacity of the small model work more effectively overall.
So less data, but easier to process for the small model.
Pretty much. It's a trade-off that pays off at smaller scales.
Yeah.
So, finding three. Small VLMs benefit from more aggressive visual token compression.
Got it. Next up, efficient image and video encoding. They mentioned splitting high-res images, but not averaging video frames.
Correct. For high-res images, they use that splitting technique, dividing it into sub-images, plus a downsized overview. Helps capture detail without token overload. Inspired by models like YouReader and SysMX.
Okay, that makes sense, but why didn't averaging video frames work? Seems like a reasonable way to summarize motion.
It does seem reasonable, but their experiments showed it actually hurt performance in the small models. It seems like just resizing each frame individually to what the image encoder expects works better for these compact BLMs. Maybe averaging loses too much specific information that the smaller models struggle to recover.
Interesting. So, finding 4. Image splitting is good for small models, but video frame averaging isn't. Just rescale the frames.
Precisely.
Now, this next one sounds intriguing. Learned positional tokens, beating simple text labels. What was the issue they ran into?
Okay, so when you split an image, you need to tell the model where each piece came from, right? Like top left corner or row 2, column 3. Their first idea was just using simple text strings like row 1 col, but they hit this weird problem they called the OCR loss plague. OCR is optical character recognition reading text in images.
No, it happened.
The training would look like it was stuck, The overall error measure would suddenly drop, but the model wasn't actually getting any better at reading text and images. It was frustrating.
Yeah, that sounds like a dead end. So what are learned positional tokens?
Instead of fixed text strings, they used learnable embeddings, essentially,
Yeah.
special codes that the model could learn to interpret as positional information. It gives the model a more flexible, nuanced understanding of the spatial layout.
And that fixed the OCR plague.
It did. Training became much more stable, and OCR performance improved significantly along with other tasks. So, finding 5. Learned positional tokens are better than raw text tokens for compact VLMs.
Clever. Okay, next. Structured text prompts and media segmentation. Sounds like giving the model clearer instructions.
Exactly. They found that using short, clear system prompts at the start, like answer the question based on the image, helped focus the model.
Like setting the stage.
Yeah. And they also added special tokens to bracket the visual content, like putting here's an image before the image tokens and given this image after.
Why? Does the model get confused otherwise?
It seems to help clarify exactly where the visual information starts and ends, especially with videos that have multiple frames. It boosted performance. They also mentioned something about training during the supervised fine-tuning stage, SFT.
Supervised fine-tuning, right?
Yes. They found it was better to only train the model on generating the answer, not on repeating the question or prompt. It forces the model to rely on the actual task content rather than just learning to copy parts of the input.
Prevents overfitting to the prompt style.
Exactly. So finding 6, system prompts, media intro-usher tokens, and training only on completions during SFT all significantly help, especially for video.
Okay, finding 7 seems odd. Reusing text data from language model training actually hurt performance. Usually more data is good, right?
Right. It was counterintuitive. They tried using text data from a dataset called Smalltalk, which was used to fine-tune large language models. They thought this high-quality text might help.
But it didn't.
Nope. It made the smaller SmolVLMs perform worse. The likely reason: reduced data diversity. The Smalltalk data is probably quite focused on language tasks. The multimodal model needs a rich mix of paired image, video, and text data to learn those cross-modal connections. Overloading it with pure text data might dilute that.
So the type of data matters more than just quantity here.
Seems so. Finding 7. Adding text from an existing LLM SFT blend was worse than using new, diverse text SFT data tailored for the multimodal task.
All right. Then there's chain of thought, or CoMT. That's showing the reasoning steps, right? Helps big models reason better.
Correct. CoT prompting involves training data that includes the intermediate steps to get to an answer. It's great for large models' reasoning.
But not for small VLM.
Not in large quantities. They found that including too much CoT data actually harmed the smaller SmolVLM model's performance.
Why? Too complex.
That's the hypothesis. The complex, reasoning-heavy text might overwhelm the limited capacity of the smaller models, potentially taking resources away from learning good visual understanding. So finding 8. Excessive CAT data harms compact model performance. They did find a tiny fraction, like 0.02 to 0.05%, was slightly helpful, but any more was bad news.
Okay, moderation is key there. And the last finding, number 9, was about video sequence length.
Yeah, they looked at how long the video clips used in training should be. Longer videos give more context, but are computationally heavier.
What was the sweet spot?
They found that increasing the average video duration up to about 3.5 minutes improved performance on both video and image tasks. Probably helps learn temporal relationships better.
But going even longer didn't help much more.
Diminishing returns. Beyond that, the extra computational cost didn't seem justified by the small performance gains for these compact models. So, finding 9. Moderately longer videos, up to 3.5-minute AVG, in training help, but excessively long ones don't add much benefit for compact VLMs.
Okay, so after all that optimization, they ended up with 3 small VLM variants.
That's right. The SmolVLM, 256M, 500M, and 2.2B models. The numbers are roughly the parameter counts in millions. 256M is the super lightweight one, less than 1 GB GPU RAM.
Random access memory, yeah.
500M is the middle ground, and 2.2B is the largest, aiming for top performance while still being edge deployable.
And the training was in stages.
2 main stages, a vision stage focusing on image text understanding, then a video stage to add video capabilities. They used a mix of datasets tailored for visual interpretation, structured data, video, and text.
So how do they actually stack up against other models out there? You mentioned the IDFix comparison earlier.
They did comprehensive benchmarks using a tool called VLM EvilKit, compared themselves against other efficient open source models like MomoE and InternVL2. The results, shown in their tables and figures, consistently show small VLM models achieving strong performance with significantly lower RAM usage.
And RAM usage is maybe a better proxy for real-world cost than just parameter count.
They argue it is, yeah.
Yeah.
Maya might have fewer parameters but still be memory intensive to run. Small VLM seems efficient in both, and yes, often beating that huge IDFix ADB model was a major highlight.
Any particular tasks where they shone?
The 2.2B model did really well on tough benchmarks like MathVista, that's visual math reasoning, and Science QA, which mixes science questions with images and text. High scores, low memory footprint, pretty impressive. And competitive on video tasks, too.
Okay, benchmarks are one thing. Did they test how these actually run on, like, normal computers or devices?
They did. They benchmarked on powerful NVIDIA GPUs, showing good scaling. But importantly, they also tested on consumer hardware, like Macs with Apple Silicon chips. The results showed that even the 2.2B model could run locally at decent speeds.
So running this kind of AI on your laptop is actually feasible.
It looks that way. They even released optimized versions using ONNX for broader compatibility. And the coolest demo was probably running the smallest 256M model in a web browser using web GPU technology.
In a browser? Wow, how fast was that?
They reported getting up to 80 decoded tokens per second on a new MacBook Pro M4 Max. That's quite usable for interactive applications. Their Hugging Snap app demonstrated this.
That really brings the on-device potential home. And people are already building things with SmolVLM.
Yeah, the community is picking it up. They mentioned Call SmolVLM for general on-device use, SmolDockling for super compact document understanding, and BioVQA for biomedical image analysis. Early days, but it shows the interest.
So wrapping this up, what's the core message we should take away from SmolVLM?
I think the biggest takeaway is that smart, focused design beats brute force scaling, at least when you're aiming for efficiency. Architectural innovation, clever tokenization, careful data curation, these are the keys to unlocking powerful, multimodal AI in small packages.
It's not just about making big things smaller, but building small things smarter from the start.
Exactly. And seeing a model under 1 GB of RAM outperform giants really drives that home.
And the implications seem huge for bringing AI out of the cloud and onto our devices.
Absolutely. It opens the door for so many real-time, low-power applications that just weren't feasible before. And making it all open source is just fantastic for pushing the whole field forward.
It's been a really fascinating look at SmolVLM. Okay, so for you, the listener, here's something to chew on. What does it really mean to have this level of visual and language intelligence running right there on your phone, your glasses, your appliances? What kinds of completely new applications or experiences could that enable? And what are the bigger societal questions that arise when AI becomes this accessible and embedded in our daily lives? Definitely food for thought. Thanks for joining us for this deep dive.